We've talked about breadth-first searches. Let's talk about depth-first searches, which have their own set of interesting properties. We have not just a distance d now. We're going to change d a little bit, and it's going to be the discovery time. And we're going to use a value f, which is called finish time. And we're going to store those in the vertices in the format d/f. We'll see what I mean in just a minute. Let's do a depth-first search starting at vertex A. Excuse me, no, let's start at C. We'll start at C. So the discovery time is going to be 1. And that's going to be a global variable, and it's going to be incremented at each operation. So my discovery time is 1. My pi value, my previous, pi is null. That's not equals, that's pi equals null. And now we'll go to the next edge, or to one of its first edge in the adjacency list. So let's go to this one, over to D. Its discovery time is 2. We'll do a slash there. And again, the previous vertex is C, on the path back to C. And now, instead of coming back to this edge to C, like we would have done in breadth first, we're actually going to process D's first edge now. So we'll process that edge. So B, its discovery time is 3. You can think of these as clock ticks. And the previous node is D. And now we'll process B's first edge. Now suppose that its first edge is this one here. We see that C is being processed, so we're going to ignore that. Suppose its next edge is this one. We'll ignore D, and we'll go to the next edge that has not been processed, A. Its discovery time is 4, with a pi value of B. Now, A is all its adjacent vertices have been processed, and so we can finish with A the next clock tick, which is 5. So A is finished. We go back to B, and everything it's connected to has been processed, so we give it a finish time of 6. We go back to D, it gets a finish time of 7. We go back to C, it gives a finish time of 8. And the tree that it creates is given in red. Right? We have that edge, and that edge. And that's the depth first search tree. Let's do another example. A, B, C. This is the same as was given in the depth first video. Okay, we're going to start at A. Its discovery time is 1. Pi is null. Let's say the first edge in the adjacency list is this one here. So that'll be in the depth first search tree, that edge right there. And B's discovery time is 2. Pi is equal to A. What's B's first edge in its adjacency list? Let's say it's that one. So C's discovery time is 3. Pi is B. And now we'll go to C's first edge, say it's that one. So E's discovery time is 4, pi is C, and it doesn't have anything to process, so we set its finish time to 5. And we go back to C. C, its next edge is here, and so D's discovery time is 6. It has no adjacent vertices to process. 7, pi is equal to C. And then C finishes 8, 9, and 10. do another example. A, B, C, D. This is disconnected. And we'll see an interesting property about depth first searches here. Now, we used a queue in breadth first search. In depth first search, we're going to use a stack. So I'm going to show the stack as we go now. So we place A on the stack, and then we'll pop A off and process it. So the discovery time is 1, pi is null. B, its discovery time is 2, pi, oh, I'm sorry. Okay, so back at A, we're processing A. We put B and then C on the stack. So everything it's connected to. Then we pop B off the stack and we process B. So its discovery time is 2, pi is equal to A, and we put anything that isn't already on the stack. Well, C is on the stack. Then we pop C off, and C is still on the stack. So we visit each edge in the adjacency list for B, and we visit this edge right here. Discovery time is 3, and pi is equal to B. Everything's been processed in C, so we finish, and finish. Now, the interesting thing about depth first search is we're going to process every vertex, whether it's connected to the original vertex or not. So we'll now process D, 7, finish time of 8, pi is equal to null. All right, let's bring up a couple of figures from the book. We'll bring up the algorithm. As well as an example. Yeah, yikes. Let's see if we can fit it all on here. Okay, so we're going to use the concept of white nodes, gray nodes, and black nodes again. And we will go through the algorithm. So we're going to initialize every vertex to white, and pi is going to be null. Now we're going to start with the vertex U, which is this one. Not very clear. And we're going to process every vertex. And if it's white, then we'll visit it. Okay, so we visit U. We set the time to be time plus 1. Now time is a global variable. And so we set U's time to be 1. I'll do this again with this figure where I can make it bigger. And then I'll set it to gray. So we set U to gray. And then we're going to look at each adjacent vertex of U and set the if the color of the adjacent vertex is white, we'll set its pi value and then make a recursive call. Now, a few minutes ago, I said we used a stack, and we're actually going to use a stack implicitly through the recursion. Okay, so we're going to make a recursive call on this node here now. You can see, hopefully, that the discovery time is 2. And now we make a recursive call. We're going to visit its first edge in the adjacency list, set the time to 3 on that, then, and mark it gray. Then we make the recursive call, visit the first edge in the adjacency list, set it to gray, update the time, make the recursive call. Now, in this recursive call, we see we only have one outgoing edge, and that's to a node that has been processed before. We're actually going to give that edge a name. That's going to be a back edge, because V is an ancestor of the current edge, or the current vertex v, X. So V right here is an ancestor of X, so we're going to call that a back edge. So we come out of the recursive call, we set the finish time, we now come out of the recursive call of vertex Y, it has nothing left to process. Same thing with V, and let's see, is there anything else to process for V? No. So we come back to U, and we see that we have one more edge to process. Now, we look at the node that we've processed, we see that it's black. We're going to call this a forward edge. Okay, so we've got the idea. Now I'm going to bring up the figure again a little bit bigger. 605, page 605. Okay, hopefully this will make a little more sense. Now we left off after finishing processing U. Now, if you'll recall, earlier I said we're going to process all nodes, and you can see that in the algorithm right here. We're going to go through every vertex, and if the color isn't white, or if the color is white, we're going to visit it. Now, we have a whole lot of nodes at this point, or a whole lot of vertices that are non-white, that are gray and black. But we do have a couple that are still white, so we're going to process one of those. We're going to start with W, and remember, time is a global variable, so we finished U at 8, now W is going to get discovered at 9. We follow an edge. Now, this edge right here is the first edge in W's adjacency list, and it goes to a vertex that's been processed. Now, the vertex is black. Before we visited a black vertex from here, we called it a forward edge. Now we're going to call this a cross edge here, because the node is not a child of W in the depth first search tree. So, and we'll see a property of that in a couple of minutes. Now we'll process the next edge here. Discovery time is 10. Z has an edge there that points to itself, so we'll call that a back edge. We finish with Z, we return out of the recursion, we finish with W, and the entire graph is processed. Every vertex is black. Let's bring up another couple of figures from the book. This shows the parentheses structure. There we go. Okay, excellent. So we've done the depth first search on the above graph. And now look at it and think, okay, well, which vertex did we start at? You should be able to see this by the discovery and finish times. We started at S. It has a discovery time of 1. What did we process next? Z. And next, Y. And next, X. X then returned, and we came out of the recursion to 6. Then we came and processed W, 7, and it finished, and finished. And then we visited the other tree. Now, let's mark in green every edge in the depth first search tree. So there are two trees going on here, right? We have this tree here. We have this tree here. Okay, parenthesis structure. Made that just a little bit too big. Let's look at S. S has a start time of 1 and a finish time of 10. So we can mark that on a timeline. S goes from 1 to 10, and we can denote that with a box. Now, S has a child in the depth first search tree, Z. So we mark that, and Z has a start time of 2, finish time of 9. Now Z has two children, 1 and 2, Y and W. Y we put on the timeline, W we put on the timeline, then Y has one child, X. And so we can see this tree coming out in the timeline. And similarly with the other tree, T with its two children, V and U. Now there is a beautiful property of this visualization and of the start and finish times. Any start and finish time is either going to be completely disjoint from another start and finish time, or will be nested in some way. So Z is nested in S. W is nested in Z. Y is nested in Z. X is nested in Y. T is disjoint from S. So in other words, you're never going to see something like this. You'll never see that. And that is further shown in what's called the parentheses property, or the parentheses structure, where if we start with a node with an opening paren, and we end the node with a closing paren, then we will have a completely nested parenthesis structure, and all of them will be balanced with each other. Now, if two intervals overlap, if they do overlap, we decided that we're never going to have that case, so one is going to be nested inside the other. If Y is nested inside Z, it means that Y is as a descendant of Z. So let's look at X. X is nested inside of S. That means X is a descendant of S in the depth first search tree. So we can see that here, child, 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 and there's X. It's a descendant. One more property about depth first search is the types of edges that we can get. So we'll come to, again, to page 607 in the textbook. Now, we have 4 types of edges we're going to talk about. We have a tree edge. And it's a tree edge when the next node is white. We have a back edge. And that's when the edge UV connects U to an ancestor V. We'll do examples of these. The next is a forward edge. I'm sorry. And the back edge, V is going to be gray. is how you can tell if it's an ancestor. Here we get a white, we get a gray. We have two more, forward edges and cross edges, and they're both going to encounter black edges. So UV connects U to a descendant V. And the way we can tell it's a descendant is the node will be black and V dot D and V dot F will be a subset, or will be contained in U dot D and U dot F. And there's one other interesting property about this, is that a forward edge could have been a tree edge if adjacency list had been in a different order. Now the last edge is a cross edge. And this is when the node is black and V dot D, V dot F is not in, the intersection with U dot V, D, and U dot F is null. In case that went off the edge there. All right, let's do an example here. Page 607. Now, we started at S, and we have this edge was first in the adjacency list. And when we visited Z, Z was white, and so that is a tree edge. Let's do this in red. Then Z visited Y. Y was white, so that's a tree edge. Y visits X. X was white, that's a tree edge. Now X looks at Z. Z is now gray. It's been visited, but it hasn't been completed. And so that's a back edge. It's looking at an ancestor. And the way we can tell that it's an ancestor is that 4, 5, the interval 4, 5 is in the interval 2, 9. So it's a back edge. Then we come out of the recursion back to Z, and we visit this edge, and it's white because W has not been visited. Then we look at this edge. Okay, so we have W, that's 7, 8. We have X is 4, 5. X has been processed, it's black. And so we know that it's a cross edge because 4, 5 intersection with 7, 8 equals the null set. Let me back up a little bit to node X. When we visited the edge back to Z, we didn't even have to check this because Z was gray, and gray is always a back edge. Okay, so back to W. Now we've processed that edge, and we come out of the recursion stack to S, and we're done with that tree. And now we're going to process T. The first one we process is this edge. It's a tree edge because V is white. Then we process V. We'll process this edge first. We see that S has been processed. It's black. And the intervals are disjoint. So it's a cross edge. And we process this edge as well. Okay, so that's the basic idea. of the edge types.